All right, let's talk crypto exams. You know that feeling, right? You see an RSA question and your heart just sinks a little? Well, you're in the right place, because today we're going to tackle that head on. We're going to break down one of the most important algorithms in public key crypto piece by piece. The goal? To turn that exam panic into pure confidence. Let's get right into it. Okay, picture this. You flip open your exam and there it is. A question that says, perform encryption and decryption using RSA. You've got your primes, P and Q, an exponent E, and the message M. And you're thinking, where do I even begin? It looks super intimidating, I get it. But trust me, it's just like following a recipe. And by the time we're done here, you are going to know every single step, guaranteed.
So, first things first, we can't lock or unlock anything without the keys, right? And in the world of RSA, that means we have to create two of them. One is a public key, which, you can share with everybody. The other is a private key, and that one you have to guard with your life. The whole thing starts with those two prime numbers, P and Q. Their secrecy, that's literally the foundation that holds all of RSA's security together.
Okay, so this is our game plan for making the keys. The exam question actually did us a favor. It gave us P, Q, and E, so steps 1 and 4 are already checked off. Awesome. So our job is to use those to figure out the rest. We need the modulus N, the special number called the totient, and then the big one, our private key, D.
All right, let's start with the modulus N. This part's a piece of cake. Seriously. You just take our two prime numbers, 7 and 11, and multiply them together.
And there you have it. 7 times 11 is 77. Easy, right? Now this number, 77, is part of our public key. And this is where the real magic of RSA security comes in. See, it's super easy for us to multiply 7 and 11 to get 77, but it is incredibly hard for even a powerful computer to take a giant number like this and figure out what two primes were multiplied to create it. That's the whole secret.
Okay, next up, we need to calculate something with a fancy name, Euler's totient. You'll see it written as the Greek letter phi. Now, don't let the name scare you. This number is absolutely critical. Think of it as the secret ingredient we need to find our private key. And the good news? The formula is super simple. It's just P minus 1 times Q minus 1. But what is this totient thing really? Well, for our number 77, the totient is basically the count of all the numbers between 1 and 77 that don't share any factors with it. They're called coprime. But hey, don't worry. You absolutely do not need to sit there and count them all by hand. That's what our handy formula is for. So, let's use that formula. We've got 7 minus 1 times 11 minus 1. That's just 6 times 10, which gives us 60. And listen, this number, 60, is a secret. It's a really important one. Because it came from our secret primes, nobody can figure it out unless they know P and Q. Okay, pay attention, because this is the most important step. This is the secret sauce. Our public key E and our private key D are like two sides of the same coin. They're mathematically linked together by that totient number we just found, 60. What we need to do is find a number D so that when we multiply it by our E, which is 13, the answer is exactly one more than a multiple of 60. It's a math puzzle, basically. It's called finding the modular multiplicative inverse.
Now for big numbers, you'd use something called the extended Euclidean algorithm. But since our numbers are small, we can kind of just figure it out. And the answer is 37. D equals 37. Let's do a quick check, right? 13 times 37 is 481. And if you divide 481 by our totient, 60, you get 8 with a remainder of 1. Perfect. It works. We found it. We have our private key.
And there we have it. We've made our keys. The public key is the pair of numbers 1377. You can post this anywhere, tell everyone, it's public. Anyone who wants to send you a secret message will use this key. But the private key, 3777, now that is your secret. Only you have it and only you can use it to read the messages.
Okay, step 1 is done. Keys are ready. Now for step 2. Let's actually lock the message. It's time to take our public key for a spin and encrypt our original message, which was the number 8.
The formula for encryption in RSA is actually pretty beautiful. It looks simple. To get the ciphertext, which we call C, you just take the message M, raise it to the power of the public exponent E, and then do all of that modulo N.
So, let's plug in our numbers. We need to figure out 8 to the power of 13 modulo 77. Now, wait a second. 8 to the 13th power is a huge number. Your calculator would probably cry. But we don't need to calculate that giant number. We use something called modular arithmetic. It's like clock math. You know how if it's 10 o'clock and you add 5 hours, it becomes 3 o'clock, not 15 o'clock? That mod 77 is our clock. It keeps the numbers manageable and under 77.
So here's the clever trick for doing this without a supercomputer. Instead of trying to calculate 8 to the 13th all at once, we break 13 down into powers of 2. So 13 is just 8 plus 4 plus 1. That means we only need to figure out 8 to the power of 8, 8 to the power of 4, and 8 to the power of 1. We do that by squaring things over and over, and, this is key, we do the mod 77 part at every single step to keep the numbers from getting massive. So we find our pieces, which are 71, 15, and 8. Then we just multiply those results together, do one last mod 77, and we've got our answer. And after all that math, what do we get? The number 50, so our ciphertext, C, is 50. Our original message, the number 8, has been transformed. It now looks like 50. It's completely scrambled. Encryption complete.
Okay, now for the magic trick. This is the moment of truth. Let's say we're the recipient. We've just received this message, the number 50. The big question is, can we use our precious private key, the only key in the world that can do this, to turn it back into what it was originally?
And take a look at the decryption formula. It should look really familiar. It's got the exact same shape as the encryption one. It's just in reverse. This time, to get our original message M back, we take the ciphertext C, raise it to the power of our private key D, and do it all, you guessed it, modulo N. So we plug in the numbers. We take our ciphertext 50, raise it to the power of our secret private key 37, and do it all modulo 77. We use that same smart trick with the powers of 2 to handle the huge numbers, and the final answer is, drumroll please, 8. We got it back. The original message is recovered. And that is the magic of RSA. It's this beautiful mathematical dance where one key locks and only its one true partner key can unlock.
Okay, so what we just did, that's called an asymmetric system because it uses two different, or asymmetric, keys. Now, a really common thing you'll see on exams is a question asking you to compare this with a symmetric system like AES. So let's quickly break down the big differences.
Really, it all boils down to one major trade-off. RSA, being asymmetric, is incredibly powerful. That public-private key pair gives you something called non-repudiation. What's that? Well, since you're the only one with your private key, you can use it to sign a message, digitally proving it could have only come from you. Nobody can deny it. The downside? All this fancy math makes RSA kind of slow. On the other hand, you have symmetric systems like AES. These things are fast, like really fast. They use the same single key to both lock and unlock data, which makes them super efficient for encrypting huge files. The catch? Well, you have to figure out a safe way to share that one secret key with the other person, and you lose that non-repudiation feature.
Okay, that was a lot. Let's boil it all down to a cheat sheet. If you're walking into that exam, these are the absolute must-knows, the things you need to have memorized for any RSA question. Right here. These 5 formulas are the absolute heart and soul of RSA. You've got to know how to get the modulus N and the totient phi. You have to understand that special link between ASCII and D using the totient. And of course, you need the encryption and decryption formulas down cold. If you know these 5 things, you can solve any RSA problem they throw at you. And that brings us to maybe the most important takeaway of all. This whole system, this amazing piece of mathematical security, it relies on one single assumption, that it's just too hard for our current computers to take a big public number and find its secret prime factors. But here's the thing. For the quantum computers on the horizon, that problem isn't hard at all. It's actually pretty easy. So as we get closer to that reality, the very foundation of RSA is starting to look a little shaky. Which leaves us with a really big question, doesn't it? What's next for our digital secrets in a world with quantum computers? But that is a topic for another day. Thanks for joining me.